The structure and domain networks are two of the building blocks of the utility network. As the name implies, the structure network is used to model the structural features that support the various types of the utility features, while the domain network contains features through which resources are being delivered. The structure network is made up of structure lines, such as this trench, structure junctions, like poles and manholes, as well as structural boundaries, such as this substation or switchgear boundary. A structure network does not have any resources flowing through it, like electricity or water, but they can contain or attach to other utility features that are part of a resource delivery network. For example, if I select this medium voltage pole here, we can see that it has two structural attachments connected to it, an overhead line end and an overhead single phase. If this pole also held fiber, you'd be seeing that listed here as a structural attachment as well. So the idea here is to maintain and manage all of your structural assets in one place, even though they're supporting assets from different domains. So the next thing we want to talk about are domain networks. A utility network can have multiple domains, but only needs one structure network. The domain network contains features through which your resources are being delivered. A domain can be made up of electric lines, such as conductors, or devices that control the flow of electricity, such as a transformer or a fuse. And we also have junctions that are placed where the features are connected. And then we have electric assemblies to represent a collection of lines, junctions, and devices, like a switch bank or a transformer bank. And finally, we have the subnetwork lines, or in this case, electric circuits that define the extent of the electricity flow. We're going to talk about those in a little bit. Next, we'll talk about asset groups and asset types. You may be wondering, how do I show all of my assets using only 8 feature classes? So all of your network assets can be captured in one of the 8 feature layers, 3 in the structure network and 5 in the electric domain network. So all of these assets in the utility network get 2 mandatory attributes. One is the asset group, and the other is the asset type. Asset group is defined as the major classification of your feature layer. For example, the electric device group has multiple asset groups such as high voltage arresters, high voltage switches, and many more. Now, the asset type represents a minor classification of your asset group. For example, this medium voltage transformer has different asset types like overhead single phase, overhead 3-phase, and so on. So these utility network feature layers are drawn as subtype group layers. The advantage of that is if I had to create new assets, these asset types are represented as distinct layers, which increases the performance of your editing workflows because a single call is being made to the data source for the entire subtype group layer. Next, we'll talk about terminals, associations, and containment. Terminals within the utility network allow you to model devices to a higher degree of realism by using terminals on devices. Now, transformers, like this one here, have defined ports where electricity comes in and electricity goes out. The utility network allows you to model these ports by using terminals on devices. The terminals are not actual features you can see in the map. They're logical connection locations from devices that allows you to control how other features connect to the device. So here we have a transformer bank, a transformer, line end, connection point, a pole, and some low voltage conductors. Now we can turn on the associations view to see how these are all connected, right? So though these devices are separated spatially, they're really connected in the back end with the utility network association. So let's take this transformer here. Now, the low side of this transformer is connected to the low voltage conductors here, while the high side is connected to this connection point, which is then connected to the line end. So the idea here is to model these devices at a really high level of detail. Certain rules can be defined at the terminal level. So I have a rule in place saying that the low side of this transformer must connect to a low voltage conductor. That's why even if I wanted to connect to a high voltage conductor, it's not going to give me this option. So let's take a look at an example of how containers are used in the map. This is one way that the utility network can manage white space. Containment associations enable modeling a dense collection of features in your network while also controlling clutter. So a good example of this would be this transformer bank. Now this transformer bank contains 9 features inside of it, right? So it has, let's take a look at our attributes. So inside it has our 3 medium voltage arresters, 3 medium voltage fuses, and 3 medium voltage transformers. Now again, the power of containers lies really with being able to visualize what's inside the container, but also the list of attributes and what's contained inside the structure, as well as seeing how everything in that container is connected. The next topic that we'll go over is subnetworks. Here we've zoomed out a bit so that we can view our entire network. Now, subnetworks are defined as a connected subportion of the network. So these are circuits in the normal electric utility language. Subnetworks are important to utility because they're going to be able to give the operations team a situational awareness of how the system is configured. At a glance of a map, the staff can understand how electricity is being delivered, and this information here is vital when recovering from things like outages or optimizing the delivery of electricity. A subnetwork like RMT001 can further be traced. So let's do that. So over here in my Find Subnetworks, I'm able to run a trace on my subnetwork. What this subnetwork trace does is it allows us to understand what assets are participating in it. Having this classification and identifying the subnetworks within a GIS is really helpful in how you manage your network. You can also take this information and export it out to a JSON file to get this information into your OMS. You can do this by running the Export Subnetwork tool. You can then set all of the different parameters that you need. It's electric. We'll do our distribution tier. Our subnetwork name is RMT001, and we're able to output this as a JSON file. Next, we'll talk about network tiers. One of the advantages of the utility network is that we're now able to trace and monitor our electric network between both distribution, transmission, and generation in the same map using tiers. So these tiers are used to organize a natural hierarchy in a domain network. In electric, they typically represent voltage or characteristics of the network. So in this electric domain network, we have multiple tiers classified based on the voltage the assets are dealing with. Distribution tier, distribution mesh, subtransmission, transmission, or generation stations. So the brightly colored lines on the map represent the distribution tier, and the darker green lines represent the subtransmission tier. And as I zoom out, we can start to see the transmission tiers that are maintained by my organization. Next, we'll talk about tracing analytics. You want to be able to understand and visualize how electricity flows in your network. The utility network provides a good framework for tracing the network and gives some out-of-the-box trace solutions like upstream, downstream, connected traces, shortest path, and isolation traces. With the device associations, terminal configurations, tier definitions, and so on, I can do good extensive tracing in my network. So the first thing that I need to do is I'm going to need to set a starting point. We'll set a starting point at this low voltage service here. I'm going to run this trace so we can now trace from a meter to a generation source, meaning we're going to be tracing all the way from a customer meter to a generation plant. So this trace is going to show me all of the features that are associated with the upstream trace. I can see, so let's take a look. We're going to set our domain network to electric, set our tier to electric distribution, and our target tier to electric generation. And let's click Run. Okay, so now that the trace has finished, let's take a look at what features are associated with the upstream trace. Okay, so over here in my attributes list, we can see all of the structured junctions. We've got high voltage poles, medium voltage poles, substations, electric bay boundaries, and here it's giving us a list of generation stations. So in this particular trace, upstream from this service meter, we can see that we have 2 coal plants and a gas turbine. So this is seeing that the customer's connected to these 3 different generation stations and could at any given time be getting electricity from one of these 3 sources. So you may be doing more extensive traces in your day-to-day operations, but this just shows you how far you can take the trace tools and analytical tools within your network. The next topic that we'll cover will be diagrams. With the utility network, you can configure single-line diagrams of your system using diagrams. So a diagram is a symbolic representation of geographic information drawn with an applied visualization technique. So here we're looking at the switching diagram for the orange circuit on the map. So these are often used to represent networks in a defined space without scaling constraints. And the utility network provides an integrated mechanism for working with diagrams. It allows you to efficiently create multi-level representations. For example, if I select a piece of my schematic on the diagram, I can then apply that to my map. So what I'm doing here is I'm propagating the selection from my diagram to my electric network editor map. And as we can see, we're now able to view all of the assets that are part of this single line on our diagram versus what it looks like in the map. Now, I could also do that same thing in reverse. Let's open up our electric network editor map. Let's select some features here, and we'll go to our utility network, and we'll be able to apply this to a diagram. So let's apply this to our circuit switching diagram. And as you can see here, it's doing the same thing in reverse. So I can readily check network connectivity as well as obtain logical views of any utility network. Next, we'll talk about network topology and attribute rules. Network rules and asset rules are user-defined rules that can be used in conjunction against the utility network and underlying feature classes. Network rules dictate which features can connect or associate to other features. And attribute rules enhance the editing experience and ensure data integrity by automatically calculating rules based on expressions or constraining acceptable values for an attribute. So I'm going to show you now what happens when I try to add in a new pad-mounted transformer and how network rules control what you can and cannot do. Now let's search for our pad-mounted transformer. So let's make sure this is the one that we need. So here is our electric device pad medium voltage transformer. Now we're looking at both an overhead and underground neighborhood. So our overhead lines are shown in the solid blue lines, and our underground lines are the dashed lines. Now here I've got my pad-mounted three-phase transformer, and I'm looking to add a new one into my map. So as you can see, as I roll over that overhead line, it's not giving me an option to snap to the line. We all know that we want these transformers to be snapped, right? So come down here and we'll snap this transformer onto this medium voltage conductor. Now I'm able to do that, but in order to continue going forward, let's we're going to need to validate our edits. Ooh, and as we can see, we've got an issue here. So I'm just going to validate those edits one more time. And so what the utility network does when you're editing is it creates what are called dirty areas. So we see up here, you can see that errors were created during the editing process. Now, I happen to know that this error is telling me that I can't put pad-mounted three-phase transformers in the middle of a span. In order to make this a valid edit, I would need to place this pad-mounted transformer at a location on the conductor where it's split. So let's go ahead and just delete that here. And we will, once we finish deleting that selected feature, we'll come over here and we'll just validate again and clean that area up. So once we've validated our network topology and we can see that everything is good, I want to take a look at how attribute rules can be configured by looking at contingent values, right? So first things first, let's go and select a medium voltage pole. I'm going to select this medium voltage pole here, and let's take a look at the attributes. So right now, the attributes of this pole are telling me that the pole is 60 feet tall, it's set extra deep in the earth, and I have a material code of precast concrete. Now, I have some paperwork on my desk that says that this pole is actually not 60 feet, but it's actually 40 feet. And as soon as I change that, we'll notice that some things have happened. So we've got these warning messages here that says the attribute does not satisfy a required contingent value, both pole height, material height, and pole depth. We also see some red outlines here where we can see that I'm violating some contingent values. And the other thing is it doesn't allow me to hit apply. So this is really forcing us to put in valid data. Now, the pole height is 40 feet, and we know that the pole is actually wood. And what the contingent values do is once you select an attribute on a feature, it's only going to give you valid choices, right? So we're going to say wood, and that's great. So, but I'm still violating one of these contingent values. So I'll come in here and say set normally in earth, and now everything is good to go, and I can continue on with my edits. I'm going to cancel out these edits because I don't want to update this map now. And that's just a small look into network topology and attribute rules and contingent values. For our final segment, we'll take a look at editing and how to use an editing feature template. So for this last part of our utility network demonstration, I want to show you an editing workflow. Now, in the utility network, there are many tools that you can use to help you to manage and streamline your editing. You can create templates that allow you to add in multiple related features at once, such as when you're adding in a new transformer bank, or maybe you're adding in a new service with a solar panel to either a commercial or a residential service. So here we can see that we have this low voltage conductor with solar template. Let's take a look at what this is going to do. So we've created this template using these builders that are going to do a few different things. It's going to drop in an overhead line. It's going to drop in an AC overhead at every vertex except at the beginning and the end. It'll drop in single poles at every vertex except at the start and the end, and a single phase residential meter at the end of the line, as well as a photovoltaic solar panel. Now you can also set up things like offsets and associations as well. So now that we've taken a look at what that template is built from, now let's see what happens when we actually add in those new features. So I'm going to come in here and I'm going to create this new template. So I'm going to snap to my transformer here, go across the parking lot, we'll take a corner and another corner. And so as soon as I'm done that, we can see that all of those features have been created. I'm going to turn off my utility network for now, and let's come in and zoom in and see what we've got here. So we can see that we have our low voltage line. We can see the poles and the other points that were put in. We've got our service meter and our solar panel. So all of that was placed with just 3 clicks. So now that I've added in this new service, the last thing that we need to do is come in and we can run this validation and make sure that everything is good to go. All right, and our validate was successful, and we've just added in all of these new assets and attributes. So this is just a small example of how editing in the utility network can be made more efficient and correct.